Hello, Math 120 students. This is 5.3 on linear programming. The worksheet is on Blackboard. You can print this or follow along with this. Let's take a look at it. Linear programming. That's what all of this graphing of inequalities is leading up to. It's a mathematical process for solving maximum-minimum optimization. So together, max-min is optimization problems which involve many variables. So notice that we've been organizing a lot of our information. We've learned how to do that. The key elements to this topic of linear programming would be the objective function, constraints, feasible region, and corner points. So we're familiar with constraints. Those are the inequalities. The feasible regions, that's the region after you do all the shading, and the corner points. Now, let's look at the fundamental theorem of linear programming. If the optimal max-min value of the objective function in a linear programming problem exists, then that value must occur at one or more of the corner points of the feasible region. If the feasible region is bounded, then both the maximum and minimum values occurs. Remember about bounded. If the feasible region is unbounded, then only the minimum value exists. All right, so we're going to do these problems with all of these directions, and you might remember these directions from the linear equalities from the last exam. This time you're going to define your variables. You know that. Write the problem constraints. That's new. These are the inequalities. Before it was write the system of linear equations. Then we're going to graph the feasible region. D, determine the corner points. E, write the objective function. F, evaluate the objective function at each of the corner points. G, write your solution using a complete sentence with correct units. Okay, there are all the directions. Those would be on the exam as well. Let's look at a problem that we're going to be facing. The officers of a high school senior class are planning to rent buses and vans for a class trip. Each bus can transport 60 students. I probably should write that or underline that. So each bus can transport 60 students, requires 3 chaperones, and costs $1,200 to rent. All right, so we're trying to figure out all of this information and the importance of it. Each van can transport 12 students, requires 1 chaperone. So a van can't carry as many students or chaperones. Those are usually the parents that come along with it. And they're cheaper, cost $150 to rent, but you can't transport as many students. And this is a senior class trip. Since there are 900 students in the senior class that may be eligible to go on the trip, the officers must plan to accommodate, here's an inequality right here, at least 900 students. Since only 51 parents have volunteered to serve as chaperones, officers must plan to have at most 51 chaperones. We're going to get back to at most and at least. That is a part of language that can be the most confusing for these inequalities. Now it says, how many vehicles of each type should the officers rent in order to minimize the transportation costs? So here is the question. How many vehicles of each type? And this is a new thing. We want to minimize transportation costs. So I want to know how many of those vehicles do we need in order to minimize our costs. So the new thing is this minimize. That is an objective, and we'll get to that soon enough. So let's look at part A. Define your variables. Well, remember that comes from the question. How many of each type of vehicle should be used? Well, what are the types? There's a bus and a van. So if I come over here, I have looked at this problem already. I let x equal the number of buses and y equal the number of vans. All right, so that is part A, same as before, where we have to define what is the unit, and it's just the number of buses and the number of vans. And let's see what B says. B says, write the problem constraints. Now these are the inequalities. So first of all, I'm going to look at my chart. And remember the chart are X and Y are the column headings, my buses and vans, X and Y. And then here are the row headings. So we're talking about students and chaperones and cost here. Okay. And you can always stop this at any time, but the buses say you can have 60 students, 3 chaperones. The vans, you can have 12 students and 1 chaperone. The cost of the bus, $1,200. The cost of the vans, $150. Now, the totals. This is where that at least 900 students and at most 51 chaperones. Now this cost is the objective. So we want to minimize the cost. And that is what our linear programming is about. It's a mathematical process for solving maximum and minimum problems. And in this case, we are trying to minimize our costs. So our cost is $1,200 for a bus and $150 for a van. Right, so I still haven't finished part B. That's just organizing my data. Now, constraints. So we're going to go 60x plus 12y at least 900. Means 900 or more. So that is going to be 60x plus 12y greater than or equal to 900. Now look at this. 3 chaperones on the buses, 1 on the van, at most 51. At most means less than or equal to. So translating at least and at most is maybe opposite of your intuition, which is called anti-intuitive. But this, you have to maybe pause this and convince yourself that this is the direction of your inequalities. Now, the other thing that we have to realize is that x is greater than or equal to 0. What is x? X is the number of buses and y is the number of vans, and you know that those values have to be positive. And this information just tells you that everything is in quadrant 1. Yeah. So those are your constraints, these two inequalities, and these two inequalities, all of these 4. That is considered constraints, and that is your part B. Now, part C, we have to graph this. So I'm giving you the window, your x-axis, number of buses, your y is the number of vans that comes from up here. X is number of buses. Well, you're labeling your axis right here, axes. So here you've got your buses, you've got your vans, and I'll give you the units here. I'd go 5, 10, 15, 20. This is 25, 50, 75, 100. And now I am going to graph these inequalities. So come up here to the first one. 60x plus 12y greater than or equal to 900. Now remember that we use our intercept. So I put 0 in for x here, and you can pause this. If you put 0 in there, it wipes that out. Divide by 12, and you get 75. Put 0 in for y into this equation. So I put a little purple dot to show you that that's going to be my purple line. And these are equal, so those are going to be all solid lines. If I put 0 in for y, right here, it wipes this out. Divide both sides by 60, and I get 15. So 0, 75 is right here. And what's the other one? 15, 0. Get a straight edge. It's hard to do a straight edge and film at the same time. Now I'm going to put my 0, 0 in to decide if I plot on this or shade on this side or this side. So 0, 0, if I put 0, 0 in here, 0, 0, is that greater than or equal to 900? No. So it's on the opposite side. So I need to shade on this side of this line. Now when you shade, just go to the line, pull. Go to the line, pull. Now you come here, the x-axis gets pulled because everything's in quadrant 1. And that is your first inequality right there. Second inequality, I'm going to do in red. 3x plus 1y less than or equal to, I put 0 in, I got 51. You can pause this and check it. Put 0 in for y, divide by 3, and you get 17. So 0, 51, about right here. Now I recommend that you put a 51 there. And then, because here 75 and 15, they're there. So this one I have to write what that is. 17, about right here. And now I'm going to try to graph this line from here to here. Okay, not bad. You can tell I do this for a living. And now I'm going to look at a little bit. This is all purple out here. This is purple in here. This is empty, empty. But now I have to shade. So this says less than or equal to 51. I'm going to put my 0, 0 in to decide which side of this red line I need to shade on. 0, 0. It is less than or equal to 51. So I need to shade on the left side of this line. So I'm going to do that. And only go to the x-axis because everything's in the quadrant. 1, okay, go to the red line, go down, red line, go down, red line, go down, red line, go down, red line. Okay, so now we have to decide where the two colors overlap. This is purple, nothing, red, but right here is where the purple and the red are overlapping. So I'm going to make this a little bit darker, a wee bit darker. And notice I have this little triangular region, which is called the feasible region. Okay, that's part C, feasible region. Now what's part C? D says determine the corner points. All right, well, look at this. It's a triangle. There are 3 corner points. There's this one, and this one. 3 corner points for that region. So I know that that's 15, 17, and some point A. So right here, I wrote down my corner points are 15, 0, 17, 0, and, ooh, how did I get 12, 15? What did I do? It was the intersection of the red line and the purple line. So here, I took the 60, 12, 900, put it here. I put the 3, 1, and 51 here. Did RREF on the calculator and got 12, 15. So those are the 3 corner points. Yeah, these take a little bit of time and you're required to do every step. So E, you're supposed to find the objective function. And I'm going to pause this because it's getting long and I'm afraid it's going to take too long to upload. So I'm going to pause here and come back for E.